Hello. Well, I'm very excited to start the tutorial. Our first speaker is Vitaly Kuznetsov. He's a research scientist at Google. He did his PhD at Courant Institute for Mathematics, and his research interests are mostly in non-stationary time series analysis in both theory and applications. No further ado.
Okay, well, thank you so much for the introduction, and I'm also very excited to talk to you today about non-stationary time series analysis. Actually, let me start by saying a few words. Why do we actually care about time series analysis in the first place, right? Why are we all here today? In fact, time series data appears in many real-world applications these days. Stock values, different other economic variables, local temperatures, or global climate trends. All of these often come in the form of time series data. In fact, I personally like to argue that all of the data that we're collecting is time series data, precisely because we're collecting this data over time, right? And if you look at this list, you'll see that actually in a lot of these applications, it is critical to be able to do time series analysis and time series forecasting accurately, right? If we're talking about stock values, then there could be millions or billions at stake. If we're talking about climate, right, it's even future of our planet. But I also want to argue that time series analysis is not only a very important problem, but it is also often a very challenging task. So let us look at maybe some examples of time series here. So, you probably have heard about Google Trends, right? So here's a plot of two time series from Google Trends. This is an interest over time in two different search terms, machine learning and deep learning. And you look at this time series, maybe you see some patterns there, right? Maybe some common trend component or any other patterns. But this initial intuition that we may have from these simple plots often can be actually quite misleading. Like, for instance, if I were to zoom in on earlier segment of this time series, say for 2012, 2013, then what I would see is a plot like that, which looks very different from my original plot. And we can see that this time series actually, for instance, also both of them look quite different, right? The machine learning time series is sort of more volatile, maybe has some seasonal component. On the other hand, deep learning is more sort of stable and doesn't vary that much over time. On the other hand, if I were to sort of progress further in time and look at the more recent data, 2016, 2015 period, then picture changes once again. All right. Now we see some sort of trends. Both time series are moving much more in a much more volatile fashion. And maybe surprisingly, even we can see that in some cases they are moving in the opposite directions, which is also something that is counterintuitive for these two search terms. So these kind of phenomena of non-stationarity make time series analysis very challenging, and it make time series analysis also very different from the usual machine learning that we're used to. Right. Typically, what we expect to see in machine learning is some sort of i.i.d. assumption. We expect that our training distribution is going to be the same as our test distribution. We expect that these distributions are fixed and do not change over time, which means they're stationary. But this is not the case for time series analysis, and in general, these assumptions are violated in these kind of scenarios. So how can we analyze this kind of data? How can we learn from this kind of non-stationary time series data? These are the kind of questions that we'll try to investigate in this tutorial and try to answer them. And the plan for today is going to be as follows. So the first thing I'm going to do is give a very quick 30-minute introduction to classical traditional time series analysis. Then we're going to have a very short 2-minute break just to catch some breath. And then we're going to discuss some more recent learning theory that has been developed for this kind of non-stationary time series. After that, after theory, we're going to take a longer break, the whole 4 minutes. And then after that, we're going to switch gears and talk a little bit about algorithmic solutions that are based on this theory that we will present. And finally, we'll discuss some connections between time series prediction and this very hot topic these days, that of online learning. All right, so let us then jump right in and let us talk about the classical time series analysis. So the way classical time series analysis works, the way this classical framework operates, is as follows. The first thing that you typically do, you postulate some parametric model that you assume is generating the data that you're observing. Then once you have done this critical step, you take the data that you observe and you use this data to estimate the unknown parameters of this parametric model. And then finally, once you have this estimated model, you use it for whatever purposes you want it to be used, namely, for instance, prediction. Right? So what kind of models are out there? Well, if you start thinking about what you're trying to do, right, somehow what you're trying to do is to use your past observations to make the forecasts about the future. Right, so a very natural thing to do would be to take, last, say, P observations, combine them in a certain way, and that would be your forecast of the future. And that's precisely what so-called autoregressive models are. They are linear combinations of your past P observations with weights A1, A2, up to AP, which we call autoregressive coefficients. And once you form this linear combination of the previous observations, yt, yt minus 1, yt minus 2, up to yt minus p, you add some noise term, epsilon t, and you assume that this is going to be the next observation in the sequence. So these noise terms that you typically add, they're uncorrelated zero-mean random variables, and they're supposed to capture the uncertainty that is not captured by the linear combination of the past observations. Right? At this point, you may say, well, why only restrict yourself to the uncertainty at time t, right? Maybe uncertainty at previous times also may play a role in this. And if you kind of start thinking along these lines, then the model that you're going to arrive at is going to be this so-called moving average model, which assumes that the observation yt is a combination of the uncertainty at time t, epsilon t, and uncertainties at previous times, epsilon t minus 1, epsilon t minus 2, up to epsilon t minus q, and they're combined with certain weights, which we call moving average coefficients. Right. And then combining these two models, the autoregressive model of the past observations and the moving average model, we arrive to a very classical and celebrated model, which is called ARMA model, autoregressive moving average model. It was proposed, I think, back in the 50s by Vitaly, maybe even earlier, and it was actually popularized by Box and Jenkins in the 70s. So let us actually look at an example of a process distributed according to ARMA model. Right, here's one. Looks like a bunch of random noise, ups and downs, some kicks. But sort of one interesting thing that you may observe is the following. If you take two chunks of this time series, right, like say an earlier chunk and a later chunk, and if you look at these two chunks, then in certain statistical sense you won't be able to distinguish these two chunks. And this phenomena is what's known as stationarity. Right, and more formally, it's defined exactly in this way. If I take any chunk of my time series and I shift it by k units, and if I look at the distribution of the original chunk, and if I look at the distribution of the new chunk, and if these two distributions happen to be exactly the same, that's what we call stationarity. In fact, this is often referred to as strong stationarity, and weak stationarity or second moment stationarity is a property that only requires basically the first and second moment of these distributions to match. Or more precisely, you want the mean of your stochastic process to be independent of time, and you want the covariance function of your stochastic process to be independent of time, which means that the covariance or correlation of any zt minus j only depends on the lag j, but does not depend on the exact time point t. So, is our original intuition about the ARMA process correct? Is it actually stationary, right? Because it seemed from the plot that I have shown to you that, any two chunks would be kind of exactly the same. So we need some tools, obviously, for this analysis, and sort of the standard tool, that you should be familiar with if you want to do anything with these kind of autoregressive models is so-called lag operator. So it's a very simple thing. Basically, what this lag operator does is that, if you're given an observation yt and you apply this lag operator L to this observation yt, then what you're going to get back is the previous observation yt minus 1. Very simple. But then what you can do, you can actually rewrite the ARMA model that we had a few slides before in terms of these lag operators. In particular, the way it's going to look, you're going to form this polynomial in terms of the lag operator, right? So on the left-hand side, I have this 1 minus AI, the sum of AI lag operator to the power of I, summed from I equals 1 to P, and I apply it to YT. And on the right-hand side, I form a similar polynomial in terms of the lag operator and apply it to the noise term. And actually, if you just work out the algebra and apply the definition of the lag operator, you'll arrive at exactly the same formulation that we had for the ARMA model a few slides before. But the reason this is nice to write out the ARMA model in this way is because it exposes interesting properties of this ARMA model in terms of the lag operator and this special polynomial that we have on the left-hand side. In fact, we're going to call this polynomial on the left-hand side characteristic polynomial, right? It's this polynomial that I denote by p here. P of z is 1 minus the sum of ai z to the power of I summed from I equals 1 to p. Right, and it precisely characterizes the stationarity properties of ARMA processes. In particular, a very standard result says the following: if all the roots of the characteristic polynomial p that we had on the previous slide lie outside of the unit circle, then the ARMA process PQ is going to be weakly stationary. Right? This is actually a very simple result, and in fact the proof of this result is also rather simple. It's just basically applying what you know about the roots of the polynomial, but in the interest of time I'm gonna skip the proof, and in fact we're gonna post the slides online, so you're gonna be able to check out the proof for yourself if you want a reference. But let us actually go back to what we started talking about originally, right? We were interested in modeling time series that are non-stationary because they're much more realistic for any application that we want to tackle, right? But we have just said that these classical ARMA models are stationary, right? Are we doomed? Can we actually change things? Can we actually use this generative framework for modeling non-stationary time series? Well, it turns out that these lag operator and this characteristic polynomial ideas allow you to also build models of non-stationary time series as well. All right. In particular, one way to do that is to use ARMA processes whose polynomials, characteristic polynomials, do have unit roots, right? They have roots that lie on the unit circle. So if that's the case, then you can factorize such polynomial into a polynomial Rz, right, which has all its roots outside of the unit circle, and then polynomial 1 minus z to the power of d, which has a root, a unit root of multiplicity 1. And if you have an ARMA process with such a characteristic polynomial, then this ARMA process is going to be non-stationary. And that's how these celebrated ARIMA models of order D are defined. So they, in a way, you can think of these ARIMA models, and I here, by the way, stands for integrated, as ARMA models of a process which applies a polynomial 1 minus lag operator to the power of d to the process yt. Right? So, take for instance a simple case of d equals 1. Right? So what ARIMA model of order d equals 1 says is that basically yt minus 1 is a stationary ARMA process. That's all it is. So how do ARIMA processes now look like? Well, if you plot one, you'll get a picture like that. That's sort of much better in terms of non-stationarity. Right? We get some, at least, stochastic trend here, perhaps. And you can keep playing this game, if you want to sort of model all other kinds of sort of non-stationarity phenomena explicitly. You can come up with all sort of extensions of ARIMA models. There is a whole zoo of those. You can incorporate a seasonal component. You can incorporate long memory. You can incorporate so-called fractional effects, time varying coefficients. There is really no limit to that. Non-linear models, etc., etc. One probably extension that any talk like that should mention is the one that tries to incorporate non-stationarity in the second moment of the time series. In other words, try to model a non-stationary variance. and that's what's known as a Garch model, right? And this model simply says, well, I want a non-stationary variance, so I'm going to assume that my variance is also a stochastic process, which is just an ARMA process. And that's how, I define a Garch model. So it was introduced by Angel in 80s, and that's what he got the Nobel Prize for. And here is an example of an ARMA process. You can see that volatility kind of changes over time for this time series. And then you can continue, coming up, as I said, with all sorts of other more fancy models. So another example is a state space, class of state space models, which you can basically think of as just a continuous space analog of hidden Markov models. Right? The way they work, you assume that there is some unobserved state xt that follows autoregressive models, right? And each next state xt plus 1 is simply b, where b is some parameter of the model times the previous state xt plus a noise term. Right? And then the observations that you actually get are assumed to be a linear combination of the state, right? So yt is equal to a times xt plus a noise term. So again, example of a particular state space process, right? And really you can continue, as I said, playing these games and keep coming up with different generative models for this. So we've talked about a lot about actually this first step in the classical framework for time series analysis, postulating a model, right? So then how can we perform this second step, right? Estimation. How do we find parameters of these kind of autoregressive or state space models? Well, I guess the first thing that you probably would think about is maximum likelihood estimation, right? Let's make a further assumption about the noise terms that we have introduced, for instance, that they're Gaussian. Then we can maybe write down the log likelihood of the data that we're observing and try to optimize the parameters of the model to minimize the negative log likelihood. For certain other models, there are also less general techniques such as method of moments or conditional or unconditional least square estimation that you can apply, for instance, to some of the autoregressive models that I mentioned. But the question is, we're not in i.i.d. scenario anymore, right? Do these methods actually work, right? Can we give any guarantees for these kind of methods? And yeah, people actually have worked on this, and they have worked out some learning guarantees for these kind of methods under some, say, additional assumptions. Like, for instance, if I wanted to give a guarantee for ARMA model that I have described to you earlier, then I would impose an assumption of invertibility, which basically means that this other characteristic polynomial that we had on the noise term in the formulation of the ARMA model has to also have its roots outside of the unit circle, and in that case the ARMA model is invertible. And if I have both, say, invertibility and stationarity for ARMA model, then I can, for instance, give a guarantee that the least square estimator of the autoregressive parameters of that model will converge in probability to the true parameters of the model. Right? So this is an asymptotic learning guarantee for this kind of models. It also requires the model to be correctly specified. but at least it gives some hope that these models can work. And I should also mention that, of course, similar. I'm talking here about just least square estimator for ARMA models, but you can come up with similar asymptotic guarantees for other models and other estimators that I have mentioned. So actually, I'm gonna. This more or less wraps up the sort of lightning fast introduction to the classical time series analysis. I just want to sort of emphasize a few things that we talked about. First of all, there are many generative models, and you can come up with a lot of those generative models yourself and model all these phenomena in whatever way you like. The learning guarantees for these kind of models that we have discussed are only typically asymptotic, and they also require the model to be correctly specified. So, they are not robust to misspecifications of the model. And finally, one of the major difficulties with actually applying these kind of models is that you actually need to come up with the model of the non-stationarity yourself. So you need to go ahead and look at the data and then say, this is, I think, what kind of non-stationary phenomena is happening in the data, and this is the kind of model that I'm going to impose. So, and then in the remaining of this tutorial, we're going to try to discuss some new theory and some new learning algorithms that would try to lift these sort of assumptions. So we'll break now for 2 minutes just for you to catch your breath, and then we'll continue with the theory part of the tutorial. Okay, so we're gonna continue with the tutorial.
Our next speaker is Mehryar Mohri. He's a professor of computer science and mathematics at the Quran Institute, and he's also a research consultant at Google Research.
All right. Thank you very much. First of all, I wanted to say that I'm really impressed to have that many people here for a time series tutorial. We knew that it was popular. Now that's just a proof. I promised to say this. This section is about theory, learning theory, and some people ask me, why do we need learning theory? And, well, the answer is otherwise you're left to do parameter search in a blind fashion, and there is no principle for designing an algorithm. Vitaly gave a description of some classical techniques in time series prediction. He also mentioned that there are some insufficiencies for these techniques. In particular, they do not have the standard guarantees that we expect for finite training samples. Their guarantees are asymptotic. They also come with a whole bunch of assumptions. So the concepts and tools that I'm going to discuss in the next few slides are hopefully going to be helpful for designing algorithms for time series in a more general way. So let me start with the formal description of time series forecasting. In that scenario, the learner receives a finite training sample, which means, a finite realization of a stochastic process, x1, y1, x2, y2, xt, yt, where the x's, the x sub t's, are in some input space capital X, and the y sub t's in the output space, the label space, capital Y. And I will be denoting by capital Z the cross product of x and y. And then we assume that we have a loss function that is bounded by 1, and that takes as arguments a hypothesis, little h, in some hypothesis set capital H of functions mapping from x to y. and, well, an element of Z, that means a pair X and Y. So the learner's problem is to use the hypothesis capital H to come up with a function, little h, that has a small generalization error, if you wish, or path-dependent expected loss. And that is defined in the bottom of the slide, and it will also give me the opportunity to describe the notation. So the calligraphic L of H, comma, bold Z1T. So first, bold Z1T denotes the sequence of the Z's, the training sample, if you wish, from 1 to T. And it is defined as the expectation at time capital T plus 1, or the time at which you wish to make a forecast of the loss of the hypothesis for that ZT plus 1 drawn from that distribution, conditioned on what you have observed so far, that means Z1T. Okay? Now, the standard assumptions that are made in the analysis of time series forecasting are stationarity and mixing. Stationarity was already described and mentioned by Vitaly. In short, it means that the distribution is invariant to shifting. Mixing is a different type of assumption, which essentially says that events, capital A, that occur after time n plus k have a dependency with respect to events capital B that occur before little n that decays with this gap little k. Okay? And this decaying dependency can be measured in many different ways. One way to do so is to use the so-called beta mixing parameter. There are many other ways of measuring that, alpha mixing, phi mixing. There's almost any Greek letter that you could append mixing to. It so happens that beta mixing is actually, one could argue, the right view. And I'm not going to detail exactly what technically beta mixing consists of, because you'll see in a minute I'm going to criticize all of these and make a lot of enemies, I'm sure. So, but before doing so, let me just say that most people who have been studying from the learning theory point of view time series, and that includes me and many of my colleagues, they have been adopting these assumptions, stationarity and mixing. And that includes the work by Vidyasagar of pack learning, where he's actually arguing that beta mixing is the right view. The generalization bounds given by U in terms of the VC dimension for binary classification, covering number bounds for regression given by Ron Mayer. We have been giving with Afshin Rostamizadeh Rademacher complexity data-dependent bounds for general loss functions, which now gives a more general view of all this. And then more recently, there have been packed Bayesian bounds given by Alker et al. All of these are making these assumptions of stationarity and beta mixing. That includes even algorithm-dependent studies, such as the study of AdaBoost by Lozano et al. Again, our study of stable algorithms in a very general way, and many other studies of this kind. All these raise some fundamental questions because stationarity and mixing, these assumptions often do not hold. They, in fact, typically do not hold. Just think trend or periodic signals. Furthermore, these assumptions are not testable. So how do we know if they even hold, right? It's even worse than this, because even if you assume that mixing does hold, make it even simpler. Assume that you even know what form that beta mixing, for example, would have. Assume, for example, that it has an exponential form. Even if you do assume that, estimating these parameters turns out to be a very difficult problem. But perhaps even worse than this is that these assumptions, these notions, do not capture some fundamental parameters of the problem, those that have structure, that means the hypothesis set, which we know in machine learning cannot be the family of all measurable functions, otherwise we cannot learn, and the loss function. So this raises some questions. Is learning with general, non-stationary, non-mixing stochastic processes even possible? And can we design algorithms that come with theoretical guarantees for such broad and general scenarios? Again, just think that those assumptions really typically do not hold. We need a new tool for this analysis. So to do so, let's just start from first principles. Suppose you have a single hypothesis H, so fix H. What are we really interested in? What we care about is the expected loss, or remember again that conditional expectation of the loss given the sample at time t+1 of forecasting. And what we receive is just training points. So the difference between the expectation, that expected loss at time t+1, and the expected loss of the same hypothesis H at time t is really the key quantity here. That is what we really care about. So of course, we're getting a full sample from time 1 to capital T, so it's the average of this quantity that becomes the really important difference that is related to time series prediction. This is for a single hypothesis. If you take the supremum over all hypotheses, this gives a definition, a quantity that we call discrepancy. And so you can see at the top of the slide, it's the supremum over all hypotheses of that average difference that I mentioned before. Notice that this quantity, unlike notions that are purely related to the stochastic process, captures the loss function, and it's directly depending on the hypothesis set. Perhaps even more importantly, this quantity can be actually estimated from data, as we will see, under some relatively mild assumptions. Notice that the discrepancy delta is 0 in the i.i.d. case. That's really straightforward to see. And one can show also that in some broader cases, for example, for weakly stationary processes with linear hypothesis and a squared loss, the discrepancy is also just 0. Okay. This definition of discrepancy is based on an average of those differences. The average here is uniform, but we might actually wish to use an even richer definition, still really geared towards the analysis of this problem, which we call the weighted discrepancy, and where now we are not just using a uniform average of these differences, but instead we use some weights, Q1, Q2, Q sub capital T, for defining that averaging. These weights, the Q sub T's, are going to be crucial, particularly when it's going to come to an algorithmic design. Why? Because you would wish to emphasize points T, XTs, or ZTs in your sample whose difference, whose expected loss is close to the time at which you're going to be forecasting, and on the contrary, de-emphasize those sample points for which the expected loss is much further away from the time of prediction. These weights Q sub T's are going to help us do this emphasizing and de-emphasizing. 2 words about this, that this definition of discrepancy or weighted discrepancy is strictly generalizing previous definitions that we have been giving still in the context of drifting with Andres Munoz Medina, or for domain adaptation with Yishai Mansour and Afshin Rostamizadeh, and with Corina Cortes, And that also is related to the notion of discrepancy or a distance that Scheib and David and others, and also Luc Deroy and others have been giving in the past. We can also give upper bounds for this discrepancy in terms of some familiar quantities, such as the relative entropy. But again, if we were to do so, we would be losing this interesting aspect of the discrepancy that is taking into account the loss function of the hypothesis set. Okay? We can also give upper bounds in terms of other quantities, such as the phi mixing coefficients of an asymptotic stationary process for, of course, asymptotically stationary processes. Okay? I mentioned that the discrepancy can be estimated. So let me discuss this here a little bit on the slide. The discrepancy can be decomposed into two parts. Suppose that you wish to make a prediction at time t+1. There's going to be some interval, say small interval of length s, just before the time of prediction, at which you don't expect the distribution to, for which you don't expect the distribution to have changed radically. So you sort of expect that the blue part, the blue arrow here, that indicates the difference between the discrepancy, if you wish, between the loss at time t+1 and the average loss within that interval of length s. You expect that not to be too large. You expect that actually to be relatively small. In fact, I'm going to be a bit further. You can prove that if this is not the case, learning is not possible. Okay? So we have to make that assumption that there is going to be some s for which this difference is not too large. Okay, assuming that now, which seems to be a natural assumption, then we can break the discrepancy into the sum of, or upper bounded by the sum of two terms. One is the term that I just described, which at the top of this slide is denoted by delta little s, s referring to the size of the interval. And the other one is the first term, which is the discrepancy between that interval of length s and whatever else you have had in your training sample. And that is the first term that you see, that delta of q up there, okay? It turns out that delta 0 of q, that delta 0 of q, which is the first term upper bounding delta of q, notice that it's all in terms of the expected loss, again, or conditional expectation, that calligraphic L. And it turns out that that term, delta 0 of q, can be in fact accurately estimated from data. Not so surprisingly, right? Because what would you do if you were to estimate it? Well, you would consider the same term with the calligraphic L's replaced by the true loss, the losses that you've observed on the sample. Turns out that that is actually a very good estimate of this quantity. Okay? So now if you use this notion of weighted discrepancy that I introduced, which again essentially comes from the first principles, and you apply some general tools that I will briefly describe, you obtain the following learning guarantee, which is very general. This theorem says that with high probability, for all hypotheses H in capital H, and for all alpha, think of it as a small number, let's say 1 over capital T or 1 over square root of T, where T is the size of your sample. So for all hypotheses, the left-hand side, that is the path-dependent expected loss of a hypothesis H, the quantity that you wish to minimize, is upper bounded by the first term, which is the weighted training loss, where the weights are these q sub t's that you might wish to play with algorithmically, plus a term that is exactly the weighted discrepancy. Alpha or 2 alpha, I already said, you can essentially disregard it as it being a small number, plus the norm of the weight vector q1, qt that you consider. Think that if you use uniform weights, that norm 2 of q is just 1 over t. Okay? 1 over square root of t. And then the square root of 2 times the log of a quantity that is the expectation of a covering number. Okay, I think I've scared you enough now. Actually, raise your hand if you're not scared yet. Okay, I managed to scare a few then. So this is the expected covering number. For now, just think of it as a measure of the complexity of the family of hypotheses, capital G, which is the family of the losses of the hypothesis little h. That's what's indicated in the bottom. This is the family of functions that are mapping z to the loss of h comma z. The exact definition of this sequential covering number or expected sequential covering number, I will try to just say a few words about it a bit later. But for now, think that this type of learning guarantee is actually not very different from what we have seen up to now. What does it say? In short, it's simply saying that the generalization error is bounded by the empirical error plus, the last term is just a complexity term, all of these familiar. The only new term, really, is that weighted discrepancy, okay, the delta of Q. It turns out that that delta of Q is really crucial. In fact, for some scenarios, say drifting, for example, you can show that you cannot do away with that discrepancy. It's essentially the best measure here that you can come up with, okay? So the discrepancy is really there. Furthermore, and Vitaly will get into the details of this sort of learning guarantees can really directly guide the design of algorithms. How? Well, the choice of the hypothesis little h and the choice of these weights Q1, Qt that I mentioned are really, really crucial here, can be precisely following this bound, if you wish to minimize this bound. Again, Vitaly will say a lot more about this. Now, there is still a problem here because delta of Q is that true discrepancy. We don't have that true discrepancy, but the good news is we can estimate it. So we just have to work with the estimate of that. Turns out, I mentioned that before, that the discrepancy can be estimated, and there is another learning bound that is in terms of the estimate of that discrepancy. So that's the delta hat of Q, which previously was denoted, which is the estimate of that delta 0 of Q. If you look at that delta hat, it's just precisely the same expression as delta 0 of Q, where I have replaced the calligraphic L by capital L. Okay? So it's just precisely the empirical version of that. So this learning bound, which only differs from the previous one by the presence of the empirical discrepancies versus the true discrepancies, is going to be a quantity that now you can directly work with when it comes to algorithms and when it comes to guarantees. This learning bound is probably the first learning guarantee that is given for general stochastic processes. There is no assumption about stationarity or mixing. The quantity really that is critical here is the discrepancy or the weighted discrepancy. And again, I've already said what I thought about the importance of those weights, okay? So if you have survived so far, you've already had the main takeaways from this theory section. But now I'm going to say a few more words, and that's only for those who can still survive, about the definition of the weighted sequential covering number. To tell you that in the case of stochastic processes, we cannot just use the standard covering number. Instead, we have to have a sequential version of that. So a weighted sequential cover of a tree is defined as follows. Suppose you have a full tree, such as the one that is displayed on the slide, and a full tree of depth capital T. And let's call that tree bold Z. That means that every node of that full tree is labeled with some element of capital Z. Z1 for the for the root, Z2, Z3, etc., etc. And what a cover of that tree is a set of tree capital V, such that no matter what path you choose in this tree, for example, if you were choosing the red path, there would be a tree in capital V, a tree little v in capital V, such that along this path, the vector v and the vector of g of z's would be very close to each other. In fact, the norm 1 of the difference of these two vectors would be bounded by alpha divided by norm of q. Okay, that's, for example, what's indicated in the bottom corner of the slide for the particular red path. Okay, so when that holds in general, that means for any tree Z where you label the tree with the ZIs, and there exists a V such that you can be close to that G of Z's along that path, when this is true every time, then the family of trees, capital V, provide a sequential alpha cover of the tree Z. Okay? So what we would want is not just any family capital V of trees. We want the family capital V of trees that has the smallest cardinality. Okay? The family capital V that has the smallest cardinality and that can cover Z is the sequential covering number of the tree Z. That's for a particular tree Z. Really what we care about is not just a particular tree Z, is the expected covering number when we take the expectation over Z, over all trees. And so to describe the expectation, I'm just going to describe it briefly on this slide. Look at the tree now that is shown here. You can play the following game. At time 1, which is at the root, you can draw two samples if you want, Z1 and Z prime 1, according to the distribution. And then if you go to the right, you can draw a Z3 and Z prime 3, again, independently, but conditioned on the prime variable, Z prime 1. If you go to the left, you can draw Z2 and Z prime 2 independently, but conditioned on the Z1, and so forth, right? So the expectation of the covering numbers that I talked about, that's an expectation over Z, where the Z's are drawn according to the stochastic process that I just described. Okay? All right. All of that looks a little bit complicated. It's not a surprise, right? We're dealing with a much, much more complex situation in the time series prediction. We're far away from the easy i.i.d. case where we can just apply blindly a whole bunch of learning theory tools. Now we have to do a little bit more work, okay? All right. So if I have still some time, and I'm not sure how much I do, I don't see anybody jumping on me, so I'm just going to say a few words. I have 2 minutes. Then in those 2 minutes, I have 15 minutes for the theory section? Oh. I have what? Okay, so you went from 15 to 2. See, this is the way negotiations go. You can see I should not negotiate anything. So I went back to 2 minutes, and that's perhaps also what you would prefer, right? We should just, you've been suffering quite a bit. Let me just say, with Vitaly, we've decided that you would have a longer break here, so you really deserve it after this, but hopefully you got the big picture. So I'm just going to give you some really just the high-level ideas for the proof of that learning bound that I just threw at you. So the way the proof starts is in the standard way of applying a Chernoff bounding technique, which consists of introducing a variable, a positive scalar t that you would wish to optimize near the end of your proof to get the best bound, and simply of applying Markov's inequality. So this part is really not so difficult. Next, you have to deal with come up with a symmetrization. And here, again, I'm just going to give you the high-level ideas. The high-level ideas and the deep techniques behind this are related to the notion of decoupled tangent sequences. For any sequence Z1, ZT, there exists a tangent, an associate sequence Z prime T, Z prime 1T, that is a tangent sequence associated to that. What does that mean? It simply means the following. The sequence z prime t is such that z prime little t and zt are independent given the path z1 zt minus 1. Okay, so imagine that you in fact draw z prime in this fashion. Whenever we have reached time t, you draw zt, of course, conditioned on what you have seen so far, but z prime t also in an independent fashion. Okay, so it's clear that you can always construct that decoupled tangent sequence. This way of decoupling, coming up with a z prime that decouples and has this independent aspect to it, is crucial to the proof and the analysis. Okay, so that's what is going on this slide. In the next slide, it's another property of tangent sequences that we're using for the introduction of Rademacher variables. And then in the last slide, we are making use of that somewhat complicated expected sequential covering number that I mentioned by applying a standard union bound. Okay, so I just gave you a very, very high level idea of the proof, but it's essentially what you would really need. And as Vitaly mentioned, of course, you will be able to look at the slides and look at the details to be convinced that indeed the proof is correct. Okay, so I'm going to stop here, and I wish you a long break. And when you come back, though, you will hear about how this theory can be used effectively to come up with algorithms, okay, that have strong guarantees now. And Vitaly would describe that. Okay, thank you.
Okay, so let's get settled in, and let's continue and talk a little bit about algorithms that one can develop based on this theory that we have discussed before the break, and I hope you're all not too scared by it. But the bad news is that actually I'll have to show a bit of theory for you again, but don't be too scared. This is just a review actually, so you should all know what it is already. Right, so it's actually exactly the same bound that you have seen before the break, right? And just to remind you what it says, right? It says that with high probability, uniformly over hypothesis set capital H, generalization error of any hypothesis little h in that set of hypothesis capital H is going to be bounded by Q-weighted empirical error of that hypothesis on the sample, empirical discrepancy, this discrepancy delta S that we hope to be small, and a term that captures the complexity of the set of the hypothesis that we're using. I would like to make two important points about this bound. First of all, we can extend this bound to hold uniformly over the weights Q in some bounded set. And second thing that we kind of tried to emphasize also before the break in the theory section is that these guarantees are data dependent. Right? And the reason these 2 points are important is because they directly motivate and help you derive some algorithmic solution to the problem of forecasting non-stationary time series. And the key idea here is to take this bound that you can actually, for each hypothesis, compute on the data, right? And try to seek a hypothesis H in the set of hypotheses capital H and the weights Q over the sample that would directly minimize the learning bound on the previous slide. Right? So this is a very general idea of the algorithm, but in the rest of this presentation I will try to argue that actually for certain very broad families of hypothesis sets and loss functions, you can solve these kind of optimization problems efficiently. Right? And the first set of hypotheses that you may think about, and the first set of hypotheses that you may be interested in, is the set of linear hypotheses. Right? So we'll consider a set of linear hypotheses with a squared loss. Right? Just to remind you, the squared loss is L of y prime is defined to be y minus y prime squared, right? Something that is very natural for the problems of forecasting. And linear hypothesis, or more general kernel-based hypotheses associated with PDS kernel K, are defined as follows. Right? We take a feature map that is induced by this PDS kernel, right? Or simply you can think maybe of a linear kernel, right? In that case, this is just an identity map, right? We map our observations X by this map phi K to some Hilbert space, right? And our hypothesis is going to be simply a linear function associated to some weight vector W, and it just takes the dot product of that weight vector W with the representation of our observation in the Hilbert space. And we'll control the complexity of this linear hypothesis by restricting the norm of the weight vector using some parameter capital lambda. And so this is a very standard set of hypotheses that is used everywhere in machine learning. So for this setting of time series sequential models, you can actually upper bound that very scary sequential covering number term that appears in the learning guarantee in terms of the parameters of this hypothesis set and the data. In particular, I give a bound here on this slide that this complexity term is bounded in terms of this parameter lambda that controls the norm of the linear hypothesis, and the radius of the PDS kernel on the data, right? The supremum of the kernel x comma x over all the x in the sample. We're also going to make another simplification, and instead of considering the empirical discrepancy directly, we will look at what's known as instantaneous discrepancy. And you can, in fact, upper bound the empirical discrepancies that appeared in our learning guarantees by the sum of qt dt, where the sum goes from t equals 1 to capital T, plus a term that captures the deviation of the weights q from uniform weights in L1 norm. And these dt's in this bound are what we call instantaneous discrepancies. And they're exactly the discrepancy between the most recent S observations that we have in our sample and an observation at time t. So that's the definition of dt for each time t. Again, I'm not going to go through the proof of this result here, but you're welcome to look at it at your free time. And this is actually a very simple result that just uses subadditivity of supremum. But what is important to actually discuss here is the computational aspects that are involved in estimating discrepancy. Can we actually compute these quantities? We said that statistically we can estimate them, but it doesn't mean that they're computable. Well, if we look actually at the definition of this, for instance, instantaneous discrepancy dt, at least in the case of this kernel-based hypothesis with a squared loss, then we'll arrive at the following perhaps also scary-looking expression. But let's take it apart, right? What this expression tells us is that to find instantaneous discrepancy, we need to solve a certain optimization problem, right? And the objective of this optimization problem that we need to solve consists of two terms. In fact, it's a different of two convex functions. Which means the optimization problem that we're going to be solving is a DC programming problem. And we can use existing machinery for solving these kind of DC programming problems to find what discrepancy dt is. But what is even more important, that in this special case of a squared loss, one can actually use special DC algorithms, difference of convex function algorithms, that would allow you to recover a globally optimal solution to this non-convex optimization problem. And this is important because it allows us to efficiently and accurately compute discrepancies that are going to be critical for our algorithms, as you will see. So, okay, let us put all of these together. So first of all, if we put all of this together for the special case of the kernel hypothesis with a squared loss function, we have this learning guarantee, which is almost the same as what we've seen before, except we replace the complexity term with this other upper bound that I have discussed earlier. And we also have an additional term in the bound that comes from the fact that now this bound holds uniformly over all the weights Q. Right? But this bound now can be computed efficiently on the data, because it's data-dependent learning guarantee and all the terms are computable. So there is a corresponding optimization problem that needs to be solved in order to find the hypothesis that is going to be used for forecasting. Right? And the objective in this optimization problem is going to consist of the following four terms that directly come from the upper bound. So the first term in the objective is your empirical Q-weighted L2 loss, right? Very natural. The second term is the Q-weighted sum of the instantaneous discrepancies that we know how to compute. The third term in the objective is a regularization term for the linear hypothesis that we're going to use. And it directly comes actually from the complexity term in the bound. Right? And the last term controls the deviations of the vector Q from a uniform distribution. And it serves as a regularization for the this parameter that we're optimizing. Right, so here also lambda 1, lambda 2, and lambda 3 are just hyperparameters that you set via cross-validation. Note that this optimization problem is joined over both Q and W. And at this moment, you may be thinking, wait a second, is it okay? Is the optimization problem easy to solve? Is it convex? And in fact, that's a very right concern. In fact, this formulation of the optimization problem is not convex, but you can alter this optimization a little bit to arrive to a convex formulation. In particular, what you can do is you can change the variables and set RT to be 1 over QT. And then if you further upper bound the regularization term for the Qs that appeared in the previous objective, then you arrive to this new formulation. And it's almost exactly as the previous formulation. We still have the first term, which is a weighted empirical error, but now the weights are 1 over RT. And this is, I remind you, a convex function in W and R because this is a square over linear function. Then the second term is this weighted instantaneous discrepancy term, but now the weights are 1 over RT. Again, this is going to be a convex function for the same reason. And the last two terms, these are regularization terms, L2 norm and L1 norm, and they are still going to be convex. So overall, we get a convex formulation for our problem. So that's nice. Let me also mention that there is another way to obtain sort of simpler algorithm that does not learn Qs and Ws together, right? But rather that does it in a two-stage procedure, and it's also going to be convex. And the way this algorithm operates is that you first just minimize your discrepancy, empirical discrepancy on the data. This way you would obtain a weight vector Q, right? And this also can be shown to be a convex problem. And once you have done that, you take this vector Q and you solve a weighted version of a kernel ridge regression problem, which is again a standard convex problem. So these are the algorithmic ideas that you can use for forecasting non-stationary time series, and we actually implemented some of these and played around with them both on some synthetic data and some real data sets. And I'll now describe some of the experiments that we've done. And let's start with just some very simple synthetic examples, just to get some intuition about how these things work in practice. So on this slide, I plot for you a very simple stochastic process, which is basically autoregression of order 1 with a slight twist. So for the first 1,000 observations, I set the parameter, the autoregressive parameter in this model to be 0.9. Right, the autoregressive coefficient. And then for the next 1,000 of observations, I switch the parameter to be negative 0.9. Right? And then at the end, I switch this parameter back for the last 1,000 observations to be 0.9 again. Right? So this way, I introduce this non-trivial non-stationarity in the stochastic process. And it's interesting to see how the estimation of discrepancy behaves in these kind of scenarios and how our algorithms work. And what we can do, we can look actually at the plots of the discrepancies that would be estimated for this kind of process. And you can see they're plotted on the left of this slide. In red, you see the estimated discrepancies, and in green this is the true discrepancy, and you can see the estimation is actually rather noisy, right? But at least it gets the shape right. You can see that in the region between t equals 1,000 and t equals 2,000, right, where I had this switch, at least the average discrepancy is much higher than in the other regions. But what's even more interesting is that these algorithms can actually be quite robust to these errors in the estimation of the discrepancies themselves. So if we actually look at the weights Qs that are learned by these algorithms, and they're plotted on the right of this slide, then you'll see that in red we have the weights that were learned for estimated discrepancies, and in green we have the weights that have been learned for the true discrepancies. You can see that in both cases the algorithm completely avoids the region where t is equal, between t equals 1,000 and t equals 2,000. Right? Which is exactly what we would desire, because in that region the distribution of the process is completely irrelevant to the most recent observations, which would be useful for forecasting the next point. And just, to wrap this section up, here are some further examples of the error plots for this artificial synthetic data. What we see here is running mean squared error. So what we do, we train our 3 algorithms, which is ARIMA, the discrepancy-based forecasting with true discrepancies, and discrepancy-based forecasting with estimated discrepancies. Once we train them on the first 500 points, we forecast the next 25 points, I believe. Then we record their error. We put these new 25 points in the training set. We retrain with this new training set. We forecast the next 25 points, and we proceed in this online fashion. And then we have this running plot of mean squared errors. And as you can see, before we encounter any non-stationarity in the data, these algorithms are sort of behaving about the same. But then once you kind of hit this non-stationarity, as you would expect, the error in ARIMA model that is not designed to handle this kind of non-stationarity blows up, but these algorithms kind of remain robust to this non-stationary change in the distribution. So to mention this, we did some also experiments with some real-world data sets, and there are some promising results there, but I see that I'm running out of time actually, and instead what I'm going to do, rather than talking about this, I'm going to invite Mehryar, and he's going to talk. Well, I mean, yeah, sure. Oh, thank you. Well, since I have some more time, we did some experiments with some data sets that we found, on the internet. These are commodity prices for different commodities, exchange rates, climate and temperature forecasting. And as you can see, from these results, we compared ourselves against a very standard baseline that people would first compare themselves as ARIMA models, and at least against those models, we never perform worse than ARIMA models, and in I think 5 out of 8 data sets here we do better. So this is the algorithmic section, and next what we're going to talk about is the connection between sort of time series prediction and this new hot area that people very are interested in these days, that of online learning. So.
Okay, so we switch gears and try now to, after this theoretical section and then the algorithms and the experiments, to talk about the connection with online learning, which, as Vitaly said, is probably one of the most important and fast-growing areas of research in machine learning. And starting by saying that there are really 2 learning scenarios for tackling time series. The first one is probably the one that we favored in our presentation up to now, and that is that of the stochastic scenario, which assumes that there is a distribution underlying the data. And there the performance measure is in terms of the expected loss, or this for us, this path-dependent expected loss. And the guarantees are, the learning guarantees are generalization bounds, such as those that I presented previously. The online learning scenario, in a way, is a much broader scenario. It is one where no distributional assumption is made. The setup is adversarial. The performance measure is based on a notion of regret. And the guarantees are therefore bounds on that regret. This is a very, very active research area. We've just listed here just some papers and names, clearly this is not covering even a small part of online learning. Definitely would wish to consult the survey book of Cesa, Bianchi, and Lugosi if you're interested in this area. There is a very rich number of papers related to this. We are favoring here some papers by Bousquet and Warmuth or Herbster and Warmuth. One reason for that is that there is a rich online learning algorithms or family of algorithms for tracking, for example, that could be very relevant for time series, et cetera, et cetera. So since I'm not sure how much the audience here is familiar with online learning, I'm going to give you probably the shortest tutorial that is possible for online learning. A 4-slide tutorial, and then we'll see how we could maybe use that to connect it with time series and solve problems in time series that we don't really know how to tackle otherwise. Okay? So let me start with the setup of online learning. In the online learning setup, it's an adversarial setting with a hypothesis set or action set, capital H. This goes over capital T rounds. At each round, little t, the player or the learner receives a point x sub t drawn from capital X. He selects in response a hypothesis h sub t out of capital H. The adversary selects some label y sub t, and the player suffers or incurs the loss of ht of xt, the prediction or its divergence with respect to the true label y sub t. So the goal of the learner or the player is to minimize his cumulative loss. The first term here in the definition of the regret indicated here at the bottom of the slide. The cumulative loss, the sum of the losses suffered over capital T rounds, minus the best cumulative loss in hindsight, looking back at the data, suffered by the best hypothesis little h taken out of a family H star. The family H star might not always be capital H, might not coincide with that necessarily. Okay? So that's the notion of regret, which says how much you would be different with respect to that reference. Here's an example of an online learning algorithm that is a very standard one based on exponential weights or exponentiated weighted average algorithms. People would refer to that as well, which is a case where you would seek to learn with expert advice. So let capital H star be a family of capital N experts, E1, E2, En, and denote by capital H the convex hull of H star. That means the convex combinations of such expert functions. The algorithm is quite simple. It's maintaining some weights, W1, W sub capital N, for the experts. And so these are indexed by the time. At the beginning, this is W1 sub I for expert I and time 1. At the beginning, they're all equal to 1. And then at each round, the expert, the learner receives xt. He predicts according to this average of the functions of the experts. And the averaging is done using these weights. He receives a true label yt, incurs the loss that is based on this function, this averaging function h sub t. And he updates the weights in this exponential fashion, which consists of multiplying the weight at time t by the exponential of minus eta, the loss suffered by that expert I. Okay? So the weight of the expert I is updated in that fashion. So if that loss is large, the weight is significantly decreased, for example. Okay? It's a very simple algorithm, but even though it's a very simple algorithm, it leads to a very strong guarantee, which is the following. if the loss function L is convex in its first argument, which would be the case for a variety of cases in practice, let's say, for example, squared error or other loss functions of that kind, and if it's a bounded loss, taking values in 0, 1, then for any sequence y1, yt, this is very strong because it's not making any stochastic assumption about that sequence. The regret of this algorithm at time capital T is upper bounded in the way that is indicated here, log n over eta plus eta t. And if you choose eta in the best way, eta is this learning rate that appeared in the exponential. It says that the regret is upper bounded by roughly the square root of t times log n. So to understand what that means, it simply means that if you choose a relatively large set of experts, so if your capital N is relatively large, then this would give you an opportunity for probably having a best expert in hindsight that has a small loss. On the other hand, you pay for this in terms of this upper bound log n, but the price to pay is only logarithmic, so it's very favorable. The regret is perhaps not even the term that you would really be interested in. It's even more precisely the regret per round. So that means when you're dividing the regret by capital T, the average regret. And here you see then at the bottom of the slide that the average regret is decreasing as essentially 1 over square root of T. Okay, so these are the type of guarantees that you would see for a variety of algorithms in online learning. Again, very general setup, very general guarantees. The proofs for these sorts of guarantees go as follows. So you define a potential. Here, the natural potential function is the log of the sum of the weights. Then essentially you prove an upper bound for this potential function and a lower bound. You compare those two and that gives you the regret bound. Here to derive that upper bound, you start by analyzing the difference of the potential at time t and time t minus 1. It gives you the log of a ratio of two weights. The denominator is the previous weights. The numerator is the new weights, which are exponentially updated. That you can relate to, in fact, an expectation in terms of some weights. You apply Hoeffding's inequality, and that gives you the type of upper bound at the bottom. You sum up these differences, and using telescopic sums, that gives you immediately an upper bound on phi t minus phi 0. You can trivially come up with a lower bound by saying that the sum can be lower bounded by a max, and that is the two lines that are mentioned in the middle of this slide. Comparing these quantities immediately gives you the bound. Okay, so this is just a very quick tour through online learning, probably the shortest tutorial you have ever heard of online learning and you would ever hear probably. This raises, though, a whole set of questions. Can we exploit both the batch scenario, the stochastic scenario, and the online learning scenario to come up with flexible algorithms for tackling time series prediction? One reason for that is that the online learning setup, as I indicated, is in fact very rich. I mentioned this way of measuring the regret with respect to the best expert in hindsight. Just to tell you a few words about this, you can extend this to the case where, in fact, you would not be just comparing yourself to the best expert in hindsight, but to a best expert that is varying over time, so to the case-shifting best expert. So it's and the type of algorithms for this sort of scenarios have been already analyzed. There's a rich family of algorithms that you can pick from. They're all simple to implement. They're based on simple updates, such as the exponential update that I indicated before. So they're really easy. It's an easy toolbox that you would wish to use. So can we use these algorithms to come up with good solutions in the stochastic case for time series? Another crucial, it turns out, usefulness or question that comes up in this scenario is that of, can we tackle some really, really difficult time series problems that up to now, part of these we have been sweeping under the carpet in a way. which are, for example, model selection in time series, or learning ensembles in time series prediction, which is a crucial problem, again, in this scenario. So let me say a few words about model selection and learning ensembles, and then see how we could gradually tackle this sort of things. Model selection is this general problem, of course, that we have in machine learning, which consists of, say, if you have capital N models, here time series models, the question is, how can we use a sample Z1, ZT to come up to find the best model, to choose among these models? In the i.i.d. case, this is a familiar problem. We have theory such as the structural risk minimization theory about model selection. And we know that, those guarantees can be approximated by using cross-validation techniques. So reserving some part of the data for validation and using that to pick the best parameter, for example. But how do we do that? How do we do validation sets, come up with a validation set for general stochastic processes in time series? How should the validation set be chosen? The last few points? If we do so, we are discarding everything else that we have seen before that could have been really, really relevant. If we choose the first few points, then we might be losing even more critical information, because that's really information that would be close to the prediction time. What else should we do? Split the data in various different ways and choose those as validation set? It's just really not clear what we should be doing. And by the way, if you hear people talking about time series and saying we're doing model selection in some way, cross-validation or something, ask them, what is it that you do? Because I bet you there is no real principle behind it. Okay? So notice that the problem can be complicated in the sense that, of course, these models have been probably pre-trained on that same training sample. Okay? There's another interesting problem that comes up if you wish to do accurate prediction, time series prediction in any kind of context, whether that is for earthquakes, as I heard a little bit from some people here, whether it's for predicting the level of battery for your system, or, I don't know, in making predictions in Wall Street. And that is the one where, imagine that you have already a family of good predictors, a family of good time series forecasters. Can you use them to come up with a good, perhaps a better, a more accurate solution by combining them, by taking a convex combination of them? A sum of QT, HT, if the HTs are your forecasters. Again, here, it's not a trivial problem, because these forecasters, the HTs, may have been even pre-trained. They could be the result of training on that sample. It turns out that both this model selection problem that I mentioned and the problem of learning ensembles, they can both be tackled and addressed by coming up with a solution to the so-called problem of online to batch conversion. Online to batch is a familiar term and problem for those of you who are familiar with online learning. But here, it's a much more difficult problem, because we are dealing with a non-stationary, non-mixing processes that are quite different from the sort of i.i.d. cases. So let me just first define what an online to batch problem consists of and how it can be tackled. But before even doing so, and just to make sure that I'm not going to run out of time for saying that, there is going to be a time series workshop here at NIPS, and I invite you to attend that. This is organized, also co-organized by Vitaly and several other people, and I will be describing in much more detail some of the solutions here and connections between online learning and the stochastic case in that workshop. So let me go back to the online to batch problem. The online to batch problem is a very natural problem. Let's denote by bold H the sequence of hypotheses that an online learning algorithm has been returning or outputting over the course of capital T rounds. So the problem is to come up with a hypothesis. Okay, so I'm a little bit confused here. Okay, so this is what the input is to the problem. That's why. That's the input to the problem. And the problem is to come up with a hypothesis, little h, in capital H, that has a small expected, conditional path-dependent expected loss using these hypotheses H1, H2, H capital T that the online learning algorithm has been producing. Okay, how do we use those hypotheses that the online learning algorithm has produced, use them to come up with a hypothesis that now has a good path-dependent expected loss? This is not anymore a matter of regret. Okay. In the i.i.d. setup, this problem is well known and has good solutions. But again, how do we design solutions here for this general time series scenario? One question is is online to batch with general non-stationary, non-mixing stochastic processes even possible? Can we design algorithms with guarantees? And here again, we need a new tool. That tool is not surprisingly similar to what we discussed before. It's similar, it's a discrepancy tool, but there is a new twist to it, because here we're not dealing with arbitrary hypotheses, we're dealing with hypotheses that are output by the online learning algorithm. So if you look at the same key difference, that key difference now is for a particular h sub t that is output by the online learning algorithm. Okay? And so when now we are taking the averaging, we're not going to be taking the averaging over that's a fixed h sub t, but the h sub t's that the online learning algorithm has been producing at each timestamp little t. And that's what the quantity that is in the bottom of the slide indicates. And that's the average difference here. That's the difference. You see the h sub t varies with time here. That leads to a notion of discrepancy, again, starting from first principles, right? That is similar to what we saw before. It's a supremum now over the choice of some hypothesis, but it's a supremum over the bold H. That means the supremum over that sequence H1, H2, H sub capital T of this weighted difference. Okay? Again, here the weights Q sub T are crucial. They're going to serve us in the same way as I indicated before to, in short, make use of the fact that some hypotheses H sub T at time T are much more useful to my prediction time at time t+1 than others, and the weights are going to help me emphasize or de-emphasize them. So this is a very natural measure of non-stationarity or dependency, as in the stochastic case. As in the stochastic case, it captures the hypothesis set and the loss function, and as in the stochastic case, it can be estimated with some mild assumptions. In fact, pretty much doing exactly the same as what I indicated before, but you'll see that there is even another way of estimating the discrepancy here, the online discrepancy, that is quite interesting. So I will briefly touch on that. And this discrepancy definition is the generalization of the type of discrepancy that I indicated before. So quickly speaking, we could use the same methods for estimating the discrepancy as I indicated before for the stochastic case. But here, there is an alternative method that is very close to the online learning view. Suppose that the loss function is mu Lipschitz. And suppose that there exists actually a hypothesis H star that has a small expected loss at time t+1. That's the conditional expectation. Let's denote by eta that expression. Disregard the little q here. It should not be here, by the way. It's not eta of q, it's just eta. Okay? So we can assume that there is a very good solution at time t+1. That means that eta, the best expectation loss, is actually small. If that is the case, then you can actually show that the discrepancy, the left-hand side in this bound, can be upper bounded by a term, the hat term, the discrepancy hat term, the empirical one, plus mu times that eta, plus a term that is small, as I indicated before, alpha, and a complexity term. Said differently, the discrepancy can be estimated here essentially by making use of the fact that there would exist a good hypothesis. There exists, but I don't need to know it, that good hypothesis that has a small error here, okay? So showing this turns out to be actually simple. You start with the definition of discrepancy. You break it into two parts to make the discrepancy expression appear. You use the additivity, subadditivity of the supremum to break it into two. You use the Lipschitzness of the loss, and then just the fact that the QT sum to 1, okay? Now, it turns out that the online to batch problem here admits a very nice solution here as well. If the loss function L is a convex loss and is upper bounded by capital M, then simply choosing a hypothesis that is the average of the hypothesis returned by the online learning algorithm, a sum of QT-HT, that sum admits a very good guarantee in the stochastic way. That means with high probability, its expected loss, path-dependent expected loss, is upper bounded by an average of the training sample losses, the sum of QT, L of HT, ZTs, plus the online discrepancy, plus a term that it depends on the upper bound of the loss and norm of the weight vector, which again you can think of as being essentially close to 1 over square root of t. Okay? So this is a strong learning guarantee for the online to batch, because it tells you that it is possible, even in this scenario, to combine hypotheses to come up with a good, accurate one. I'm not going to go through the proof, but it's just really 2-3 lines. What is even stronger is the following guarantee for, again, in the case of the convex loss function, which says that for the same hypothesis H, the path-dependent expected loss can be upper bounded by the loss of the best expert, the best sequence, H star, plus the discrepancy, plus a term that is the regret per round, which we showed can be upper bounded in many cases in online learning by a term of the form 1 over square root of t. And other terms that you saw appearing already in the analysis that Vitaly showed in terms of the weights that are used in the stochastic case, okay? So the high-level idea here is that online learning can be used to produce a sequence of experts, H1, H capital T. Those experts can be combined using some weights Q1, QT to come up with a very strong hypothesis in the stochastic case. The guarantee for that hypothesis is given here. Same story as before. We can choose those weights Q1, QT in the best way to minimize that upper bound. These are things that I will be able to describe in more details if you attend that the talk I will be giving in the workshop. Okay? I'm going to stop here and conclude with the following remarks about time series. Time series forecasting is a key learning problem in a variety of important tasks. Vitaly mentioned many of them in the beginning. Most of the data that we are facing today are in fact sequential in nature, so time series would be the natural way of formulating the problems. At the same time, time series prediction in the most general case is a challenging problem, both from the theoretical point of view and the algorithmic point of view. If you want to come up with good solutions, accurate solutions, and solutions for which you can give guarantees, okay? This is, of course, a very challenging problem also in applications. And you know that in a variety of cases, people would want to have very accurate solutions for a variety of tasks of this kind for sequential data. What I presented, Vitaly and I presented, is a series of learning guarantees, data-dependent learning guarantees, for the very general case of time series prediction, non-stationary, non-mixing, no assumption, the notions of discrepancy that you heard multiple times in this talk are really, really crucial for tackling this problem, both from the theoretical point of view and the algorithmic point of view. We discussed algorithms, guarantees, and showed also that these algorithms in practice can be effective. The combination of online learning and batch or stochastic prediction leads to a whole other set of very, very interesting solutions. I tried to say a few words about them to sort of tell you how this could be done. In particular, this can be used to solve problems that are really difficult. We don't really know how to tackle them otherwise for model selection or learning ensembles. Again, these are things that I could talk about a lot more. And let me finish by further advertising this workshop. It's Friday and it's in room 117. Okay? Thank you.